All right. I'll get started. We begin with a word of prayer. So, Dear Heavenly Father, we thank you for this day. I thank you again for these students and for this class. Just ask you to bless our work today. Help us to understand a little bit more about your creation, about one-to-one functions and all that, and just to encourage the students just to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen.
Amen.
All right, so let's see what I got here. So we've talked about rational functions, how to graph rational functions, and we've talked about polynomials.
Sorry.
And now, in this part of the course, we start talking about the inverse of a function, all right? And so to understand what the inverse of a function is, we have to first understand this so-called one-to-one property. So let's talk about this. So, hilarious, but anyway. So one-to-one property is this. If f of A is equal to f of B, then A is equal to B. This is the so-called one-to-one property for a function. If you have two outputs are equal, then the inputs must be the same. All right, and when this holds, so that and that has to hold for all A and B in the domain of F. So this is the one-to-one property. Now let's draw a picture of this and see what this means. So because there's a graphical test we can do here.
Oh, let me. Oh, we go.
So suppose the graph looks something kind of sort of like this. All right. If that's the case, notice what happens here. If we look at a particular horizontal line, all right. What is so funny? Let's see here.
Horizontal lines, I guess. I'm not the only one with problems. I'm sleepy.
Am I going to have to separate you three? I can assign seating in here if I need to.
Oh my gosh.
We were having a really serious debate. So anyone needs to know, Girl Scout cookies go on sale this February 16th. We had a whole debate on whether it's called a Samoa or a delight.
Ah.
Yeah, which one is it?
Crazy.
Okay. So look at this. So this is A. This is B, right? And if that's a horizontal line, this point is what? This point right here would be A comma f of A, right? And this point right here would be B comma f of B by the definition of what does it mean to be on a graph, right? The graph is the set of points such that y equals to f of x. So if this is the situation, what do we have? We have f of A, right? We have f of A is equal to f of B, and it does not imply A equals to B, right? So what would that mean? So this function does not have the one-to-one property. So to have the one-to-one property for f, this would mean that f is a 1-to-1 function. So the function which I have graphed here is not a one-to-one function. Why? Because we have a horizontal line that goes through two different points on the graph. that means that there are two different inputs which output the same output, right? So in this case, we say that this function fails the horizontal line test. So the horizontal line test is simply this. A function passes the horizontal line test if there is no horizontal line which intersects the function in more than one point. It's okay for the horizontal line to not intersect the function anywhere, that's fine. But what we can't have is the horizontal line which intersects the graph of the function at multiple points. If you have that, it's not a one-to-one function. So let me give you another example here.
Let me take a picture.
So if the function looked like, let's say, this, all right, so here's a graph, y equals f of x, then this function would be one-to-one because, you see, if we look at any possible horizontal line, what happens? It only hits it once, that's right. Like this, just 1 point, just 1 point, 1 point. Each horizontal line hits the function's graph just 1 point. That is a one-to-one function. Passes horizontal line test. F is one-to-one function.
Professor,
Uh-huh.
mind if I ask you a question?
Yeah, ask away.
So I'm really sleepy right now.
Uh-huh.
Could I take the pictures so I can write them down?
Yeah, you can do that. That's fine.
Because I am creating a formula sheet early.
Well, that sounds like a good idea. All right, so sometimes we have to summarize here, guys, if we have the graph of the function, we can see whether or not it's one-to-one by just looking at the horizontal line test, right? Or if the function is something that's really easy to graph, we can create the graph and decide whether or not it's a one-to-one function, right? Like, how about this? Example 1. What if we had, I guess this is example 1 and example 2, isn't it? So example 3, I won't give you the graph, but I'll let you make it up. How about this? Suppose we have f of x equals to 3 minus x squared. Is this function one-to-one?
No.
Why?
Oh. This. This is not a one-to-one function.
But why is it not a one-to-one function?
Quadratic.
It's a quadratic? I like that. What's the graph of a quadratic look like? What is it?
So it does pass the vertical line test.
Yes, every function passes the vertical line test. The graph of the function does. But this is a new thing. This is a horizontal line test. There are some functions which pass the horizontal line test, and there are some which don't. And this one doesn't. So yeah?
It can't because it's an even function. So that means that it can't be a one-to-one because there's going to be some.
Good point. Yeah, good point.
That duplicate.
That's actually a very good point. He's saying that an even function can't be one-to-one, right? Does that make sense? Even function, by definition, has what? F of x equals to f of minus x, right? If that's the case, that right there shows you that an even function is not one-to-one, right? Because is x equal to minus x?
No.
Well, usually no, right? What's the one case where that's equal is x equal to 0. But if the function in question has a domain which is symmetric about the origin and includes something other than 0, then yeah, an even function is not one-to-one. This is an even function. So just to the point here, if we look at this, there it is, right? Fails horizontal line test. Not one-to-one. Not one-to-one function. Now let me show you something a little bit sneaky. Check this out. What if I add some terms and conditions here? What if I say f of x is equal to 3 minus x squared, all right? But now I have the domain of f is equal to, let's say, 0 to infinity. Now is the function one-to-one? The answer is yeah, because I just did what? What did I just do?
You limited the domain so that the negative x's don't apply.
Right, I just got rid of all the minus x's, so to speak. So now it's just half of the parabola, right? It's just this. And now, hooray, it passes the horizontal line test. So wait a minute, that's weird, isn't it? So so we pass horizontal line test. F 1 to 1. Now, actually, what I should let me not call this F. Let me call this one G, if you guys don't mind. I'm going to call this one G. And let me share with you something that I don't always share with college algebra, but it feels right to tell you guys today. That the function in example 3 and in the function in example 4, they're related. And what we're doing here, there's a formula for this. I mean, a notation for this. What G is equal to F restricted to 0 to infinity. So this is the so-called restriction of F to 0 to infinity. This is a game we can always play with a function. We can take the domain and we can make it smaller if we like. And we just use the same rule for the function, same formula, right? But the inputs that are allowed are restricted. So you can kind of see that the problem of a function not being one-to-one, you could fix it sometimes, right? If you do what? You just throw away the part of the function which doubles up on the y values, right? Like just look at a narrow enough part of it that you don't circle back to the same y values. All right? So that's about all I have to say about the graphical aspect of it. Let's talk about the algebraic way of checking for one-to-one. So example 5. Suppose we have f of x equal to, let's say 3x minus 1 over x plus 2. All right? Is this function a one-to-one function? Now we could graph it. We could do that, but let's not. Let's instead check if it's one-to-one by direct algebra. And so to check one-to-one by direct algebra, what we do is simply set f of a equals to f of b, and then we try to see if that implies a equals to b. So let's try it out. F of a equals to f of b. What's that give me? That tells me that 3a minus 1 over a plus 2 is equal to, well, 3b minus 1 over b plus 2. Now what we want to do is show that that equation implies a equals to b. How do you do that? Well, let us multiply by the denominators, right? Let's cross multiply. So this gives us that b plus 2 times 3a minus 1 is equal to a plus 2 times 3b minus 1. All right? That's my step number 1. Get rid of fractions. As you guys know, we hate fractions. Is hate too strong a word?
Strongly dislike.
It's strongly dislike. I think I hate them with a pure hatred. No, I devote them to destruction. We're going to go Old Testament on fractions in here. We'll preach imprecatory psalms against the fractions as is needed. Grind their bones, break their teeth, all that kind of stuff. So multiply it out, what you got? You know, the part of the Old Testament they don't teach anymore. Let's see here, 3ab. You FOIL this out. 3ab, Michael, you're cracking me up. 6a minus b minus 2 is equal to 6ab plus 6b. My bad. Yeah, plus 6b minus a minus 2. All right, so I just FOILed it out, both sides, multiplied it out. Now there's some common terms there, isn't there? See what we got in common? See, we got this guy here, but we've also, oh man, come on, look at that. How did I get a 6?
That's what I was about to ask. This 6 comes.
Yeah, follow man. There, that's better. Yeah, because a times 3b is 3ab.
Just sleepy.
You should sleep sitting down. If you sleep standing up, you're going to get hurt.
No, it's just that never mind.
So the 3ab's cancel. You're killing me, Michael. 3ab's cancel. Oh, and we got a minus 2 on both sides, so add 2 to both sides. That's dead to us as well. And, okay, so now bring all your a's to one side and all your b's to one side. What you got? You got yourself 7a. We've got 7a is equal to 7b, right? Which then tells us, lo and behold, a equals to b. Hooray! We have shown through direct algebraic argument that this function is 1-to-1. All right? Question? Comment?
When am I going to get my test back?
You think I've already graded the test, Michael? Goodness gracious. Let's see here. Now, come on. Let's work another one of these. So, what if we had example 6? Suppose we're looking at f of x equal to 3x squared minus 8. Is this function 1-to-1? I mean, this one we could do the graphical thing, right? You know it's a parabola. It's not going to be 1-to-1. But let's work it out in the algebraic way, okay? So algebra, we set, is this function 1-to-1? So let's begin by supposing f of a is equal to f of b. So that tells me 3a squared minus 8 is equal to 3b squared minus 8. Can you guys solve that? I mean, what does that say about a and b? Can you guys, what do we get pretty soon? We get a squared equals to b squared from that, right? Do you guys see it?
Yes.
Yes? All right. How do we, so if we have a squared equals to b squared, there's a couple different ways to go from there. How about this? We've got a squared is equal to b squared. What does that tell me? That implies that a is equal to plus or minus b. Right? Using the square root property? Ah, but what's the problem with that? So that tells me then that f is not 1 to 1. Because it doesn't force a to be equal to b, right? Do you guys get it? Let's do another. Example 7. Suppose we had f of x equals to the cube root of 3x squared. Well, let's not do that 3x squared. So it's 3x plus 20 there. Is this function 1 to 1? Let's see if it is by algebra. So we set. Notice that the starting point of the algebra is to suppose. We suppose f of a is equal to f of b. That's the starting point. So like on the next test, I know it's a ways away, but if you're asked to show that the function's 1 to 1 algebraically, you have to know the starting point. The starting step is assume f of a is equal to f of b. You go from there. If you don't have that clear in your mind, you'll just write something nonsensical down. I don't know what you'll write, but it won't be right. So we begin with suppose f of a is equal to f of b. All right, and that here tells me that this cube root of 3a plus 20 is equal to the cube root of 3b plus 20. All right, wonderful. What's the natural enemy of the cube root? Yeah, the third power, the cube, right? So this gives us that the cube root of 3a plus 20 cubed is equal to the cube root of 3b plus 20 cubed, which of course gives us that 3a plus 20 is equal to 3b plus 20. All right, and then what? Why is it so hot in here? I'd say I'd get over it, but it's not true. Math needs to move to one of these new buildings with their fancy new air conditioning and temperature controls and such. I've heard tell of the music building being delightful. Math is music, right? Some ways it is.
Please don't ruin music.
Please don't ruin music. How dare you, sir? How dare you?
That's it, I failed.
Lo and behold, a equals to b, therefore f is a 1 to 1 function. Do any of you guys know any math majors? Yes? All right. If you want to impress them, tell them that today in college algebra, you learned about injectivity of functions. So 1 to 1 function, aka injective function. I'm only telling you that because you have a math major friend that you might want to impress. You say, oh yes, we learned about injectivity today in college algebra. They'll be like, huh? And also make sure that when you talk to this person, yeah, he was showing us about restrictions of functions and injectivity. They'll be very impressed. They'll be like, how dare he? Yeah, those are big words. But that is what we're doing. We just call it 1 to 1. And we either talk about the horizontal line test or the algebra test, all right? Okay, so, and we could look at the graph of the cube root function and see why this is, right? A cube root is like a cubic function turned sideways.
Can I use the bathroom real quick?
Sure.
Thanks.
So, on its lonesome, I don't think this is terrible. I mean, it's interesting as much as it is, but what's more interesting is how this ties into the concept of an inverse function. All right, so let's talk about that. What's an inverse function? So, and before I even define that, let me ask you a question. What is a function? Like what is the important property that a function has to have? If I give you an input, how many outputs do you get? Give back to me. If you're a function. One output, right? Not two, not three, not infinitely many. Just one. So a function has to be single valued. So whatever this thing is that I'm about to define, if this inverse function is a function, it has to be single valued. And it turns out that's the reason that we need to talk about one-to-one. So here's a picture. If we've got if this is A, and over here is B, and my function goes like this, all right? My function goes from A to B. How should f inverse go, do you think? The opposite way, right? So the inverse function undoes what the function does. All right? So here's the inverse function. Go like this. So the function that we're given goes from A to B. The inverse function will go from B to A. All right? And immediately what this means is that the domain of the function is equal to the range of the inverse function, and vice versa. The range of the function will be equal to the domain of the inverse function. So that's one of the basic things. And we also have a couple defining relations, okay? So here's the definition essentially. If f from A to B is one-to-one function with range of f equals to b,
Did I miss anything?
of course, then
What?
f inverse
We're talking about inverse functions now.
is a function from
Example 8.
b to a.
You just explained.
We're defining inverse function at the moment.
All right.
Don't worry, it's not done yet. So Michael, I was just telling them that the function goes from A to B, the inverse function goes from B to A, and the inverse function basically undoes what the function does, all right? So to write that down systematically here, here's how it goes. When y is equal to f of x, then x is equal to f inverse of y. That's how the inverse function works. If the function starts with x, right, and it maps over here to y equals to f of x, then the inverse function takes that y and moves it back to x. That's what it does. Now, let me give you some more specific equations here. What we have is we have f of f inverse of y is equal to y for y in the domain. Excuse me, for each y in the range of f. And we also have that f inverse of f of x is equal to x for each x in the domain of f. All right, that's the definition of an inverse function. So do you guys see why the one-to-one property is important here? Let's think through it. What would happen if I had y equals to f of x? If I had two different y's that worked for that one x, what the trouble would be then? Logically, I wouldn't know, which x to put over there, right? But the fact that the function's one-to-one means that there's no ambiguity in putting the x over here like that. So we need the one-to-one property in order for the inverse function to exist. So like I cannot find an inverse function for the example 3. I can't find an inverse function for example 6. But we'll see we could find an inverse function for like the formula from example 4 or from example 7 or example 5. All right? So this is the definition of inverse function. Let me share with you how we actually find the formula for the inverse, all right? So I'll share with you my algorithm, if you will. So what example am I on? Well, I guess this isn't an example. So here's the algorithm for finding formula for F inverse. All right, number 1, you're given f of x. All right, so you have to be given a formula. All right, set y equals to f of x. Okay. Step number 2. Let me call this equation here star. Number 2, solve star for x equals to stuff in y. All right. Step number 3, f inverse of y is equal to stuff in y from the previous step. Done. There you go. That's the formula for the inverse. Now I'm assuming what? I'm assuming it's a one-to-one function. Actually, if you try this algorithm out on a function not knowing whether it's one-to-one or not, you'll get stuck in the process of solving for x. You'll find out you can't solve for a unique x. Right? And there's a step 4. Step 4, swap y to x if you like, if you need, to give f inverse of x. Like if you're interested in finding the formula for the inverse in terms of x, I say step 4, swap x and y. Now, if you think back to how you were taught this material before by some other instructor, like in high school or something, odds are very high that the first step that they did was what? Swap y and x. That's what's typically taught. And the reason they do that is because they are only willing to think about functions of x. All right? But I have a higher opinion of you guys. I think you can think about functions of y. I think it's okay. And so I am content to ask you questions about finding the inverse as a function of y. I also like that if we write f inverse of y, it emphasizes the fact that where x comes from and where y comes from are different sets. X comes from the domain, whereas y comes from the range, and those don't have to be the same set at all. So example 8, let's suppose f of x is equal to 3x minus 2. See if you can calculate the inverse formula for that. What's the formula for the inverse function there? So try to follow my algorithm. Write down y equals 3x minus 2. Can you solve that for x? Surely you can solve that for x, right? Let's try it out. Y equals to 3x minus 2. Isolate x. We got what? 3x is y plus 2. Divide by 3. X is y plus 2 over 3. There is your quote-unquote stuff in y that I was talking about. And behold, f inverse of y is equal to 1/3 of y plus 2. Hooray. There you go. That's your inverse function.
Okay.
Excuse, can I take one of my final pictures? Thanks.
Oh, that, okay, that makes sense.
What would the formula for the inverse function as a function of x be, if you wanted it? And why would you want, on this matter, why would you want to write the formula as a function of x, perhaps? What are we used to doing with functions of x? One reason you might want to write the formula as a function, the inverse function as a function of x, is so that you could graph both of them, right? We could graph both f of x and f inverse of x and compare how they look. We could do that here, right? Let's do.
Why does it work to be inverse of x as opposed to just normal function of x?
I'm sorry? Why is what?
As you just wrote it, changing it to x. Why does that work? I thought it was for inverse function you had to use the range to plug it to the main or.
Well, you can switch the letter to whatever you want. I can write f inverse of Pac-Man if I want. But if I want to graph f of x and f inverse of x on the same graph, I need to use x for both functions. So, listen, the 3x minus 2 has a y-intercept of minus 2 and a slope of 3, right? So it's something kind of sort of like this, roughly speaking, right? And what's the other one? 1/3 of x plus 2. What's that do? It's got an x-intercept of minus 2, doesn't it? It's got an x-intercept of minus 2, and it's got a slope of 1/3. So
it's the opposite.
it's something like that, right? So there's your, what's the relation between these two graphs? Can you guys tell me?
They cross.
Okay, where do they cross?
Oh, I remember it.
You remember it.
They cross
Well, how do you, I haven't talked about this before. How are you remembering it?
with,
From a previous math class?
yes.
You've talked about math to another person other than me? How dare you? You've been cheating on me. Let's see here. I'm very unfaithful. So that's that's the line y equals x. And if we do our job correctly, what you should see is that the graph of the function and the graph of the inverse function are related by reflection over the line y equals x. To be more technical, here's a theorem. If a comma b is in the graph of f, then b comma a is in the graph of f inverse. And yes, it is hot in here. Oh yeah. Yes, Michael, agreed. So like for instance, a specific application of the theorem, this point is 0, minus 2, right? This point up here is minus 2, 0. And there's one place where they intersect. Right? Yeah?
1, 1.
They intersect at 1, 1? Oh yeah. Hey, good job.
Thanks.
Did you just guess that or you worked it out?
Just guessed it.
Good. Yeah. Usually I have to do algebra to figure that out, all right? So let's recap. If the function is 1 to 1, we can calculate the inverse through this algorithm. And if we want to, we can understand the graph has to be related to the given graph by reflection over the line y equals x. All right? I'm going to be repeating all of these things next class. So if you already understand them all, I'm sorry, you're going to be really bored next class. But let's go on here.
I'm gonna need to repeat because I was.
You need to repeat because you're sleepy. Well, maybe next time you won't be sleepy, right?
Yeah, I'm sorry.
You're sorry. It's okay. So example 9. Oh, here, how about this? Give me a second here. I have to look this up. Formula for Fahrenheit in terms of Celsius. All right, here we go. The formula for Fahrenheit in terms of Celsius. Come on, stupid phone. Give me the formula. So annoying. All right, so 30 times the degrees, 30 times the centigrade. My bad, not 30. I'll get it eventually here. 1.8 times C plus 32 is equal to Fahrenheit. For example, that right there, this tells you what? So we can think of it this way. F of x is 1.8 x plus 32. And here, x equals the degrees centigrade, right? And y equals to f of x would be degrees Fahrenheit. For example, what happens if you have 0 degrees centigrade? That's freezing, right? What's freezing in Fahrenheit? 32. See how the formula works? Yeah. So if we calculate the inverse function here, we get 1.8x is equal to y minus 32. Divide by 1.8, right? And so there you go. F inverse of y is equal to y minus 32 over 1.8. And I think this is a good example of where you really do want to use a different symbol for both the domain and the range, because they have different meaning, right? X is the degree of the temperature in terms of Celsius, whereas y is the degree of the temperature in terms of Fahrenheit. But just like my graph above, there's some point, if you were to graph both in terms of x, right? There's some point where the degrees Fahrenheit equals the degrees Celsius. Did you know that? So if we set, you know, x minus 32 over 1.8 equals to 1.8x plus 32, and you solve this equation, you'll get x equals to minus 40. So minus 40 degrees Fahrenheit is actually equal to minus 40 degrees Celsius. That's where the two temperature scales match up as it happens. Anyway, I like this example as just as an example of why you might want to use a different symbol for a different, you know, function. Because people always ask at some point or another, why are we doing this? What does this matter to the real world? All that jazz. So, I actually do have your test graded. Let me get back to you.